Now see, the next phenomena which we have to study in wave optics, that is diffraction. Now diffraction means what? When waves encounter to any obstacle, it implies when the wave is passing through the slit, we can say like that. Okay. So slit is the obstacle. So through the slit, when it passes at the time from the edge of the obstacle, bending of waves takes place. And this bending of waves, that is called diffraction. That is called diffraction. And the scientist Grimaldi very first observed this particular phenomena. Now here we have to give one thing in our mind. Diffraction was obtained experimentally first. And then after those experimental observations were explained with the help of theory. ઓકે, એટલે આ વસ્તુ માઇન્ડમાં રાખવાની કે પહેલા એક્સપેરિમેન્ટ થયો હતો અને એક્સપેરિમેન્ટલી ડિફ્રેક્શન ઓબ્ઝર્વ થયું. એટલે જુઓ મેં અહીં તમને બતાવ્યું છે કે ડિફ્રેક્શનમાં શું થાય. ઓકે, સી સપોઝ હિયર light is passing through this particular slit. હવે લાઇટ જ્યારે આ સ્લીટ ઉપર પડે ને ત્યારે after all we can say the wavefront incident on the slit. Now each and every particle on the wavefront behave as a secondary source. હવે એ બધા જ પાછા પોતાનામાંથી સ્ફેરિકલ વેવલેટ્સ જનરેટ કરશે. હવે એ સ્ફેરિકલ વેવલેટ્સ આ જે ઓબ્સ્ટેકલ છે એની સાથે જે કોન્ટેક્ટ એસ્ટાબ્લિશ કરશે એ અલગ અલગ હશે. બરાબર છે? એટલે ડિફરન્ટ waves produced will be deflected, or we can say the bending of different waves will be different one, or we can say different waves will be deviated at different angles. હવે આપણે અહીંયા આગળ કોન્વેક્સ લેન્સ મૂકી અને એને જો સ્ક્રીન ઉપર ફોકસ કરીએ, then we can observe this thing at the center, means this O, which one is on the normal bisector to this particular slit. There you will get the maximum intensity on the screen, which is known as central maxima, which is known as central maxima. Then after, on either side of this central maxima, you will get dark bands, means minimum intensities, which are known as first minimas. Again, on either side, you will get the intensity of light, which is known as first maximas. But here, the intensity of first maxima, that will be very much less than the intensity of central maxima. Then again, either side, you will get minimum intensities, which are known as second minimas. Then again you will get maximum intensities, so are known as second maximas. But again, the intensity of second maxima, that will be very much less than that of first one. તો આ ટાઈપનું તમને એક્સપેરિમેન્ટલ ઓબ્ઝર્વેશન્સ મળે જ્યારે તમે એક્સપેરિમેન્ટલી લેબોરેટરીની અંદર લાઇટ વેવ્સનું ડિફ્રેક્શન સ્ટડી કરો ત્યારે. ઓકે, તો હવે આનું એક્સપ્લેનેશન કેવી રીતે અપાય થિયોરિટિકલી. ઓકે, ચલો અહીં સુધી ક્લિયર. Now see, we can give the explanation of central maxima like this. here all those waves when are passing through the and are not deviated, એટલે કે જ્યારે આ સ્લીટની અંદરથી પાસ થતા હોય ને ત્યારે આ સ્લીટની જે એજ છે જેને આપણે ઓબ્સ્ટેકલ કહીએ એની સાથે ટચ જ ના થાય એવી રીતે અહીંથી પાસ થઈ જાય તો એનું ડિફ્રેક્શન નહીં થાય. So when all those waves which are not diffracted, when superposed here, at that time the path difference between those waves superposing at point O, that will be equal to 0. So constructive interference will be formed, and due to that the maximum intensity of the light will be obtained at this particular point. So in this way we can give the explanation of central maxima. Clear? Now some waves are diffracted at such angle theta for which slit behave like divided in two parts. Slit behave like divided in two parts in such a way that the wave diffracted from the edge of the slit, means as shown in the figure, at point L, and the wave diffracted from the center of the slit at point A. These two waves, when superposed at a point on the screen, at that time the path difference between those two waves, that becomes lambda by 2. So they produce the destructive interference, and so that the intensity will be 0. Now for each and every wave diffracted from this first part of the slit, LM, its effect will be cancelled by the waves which are diffracted from the second part of the slit, MN. એટલે કે આ LM પાર્ટમાંથી જે waves આવશે diffract થઈને તો એ દરેક વેવને કોરસ્પોન્ડિંગ આ MN પાર્ટમાંથી ડેફિનેટલી એક ડિફ્રેક્ટેડ વેવ એવું હશે કે એ બેના સુપરપોઝિશન માટે પાથ ડિફરન્સ લેમ્બડા બાય 2 થાય. તો હવે બ્રોડ સેન્સમાં આપણે એવું કહી શકીએ કે the effect of all the waves coming out from this first part of the slit will be cancelled by all the waves which are diffracted from the second part of the slit. So at a point on the screen we get the dark band. Clear to all of you? Now suppose the width of slit is A, and here see the waves diffracted from L, M and N are represented in the figure. Now draw normal from L to the wave which one is diffracted from N. So that is LQ. Now after this LQ, all the waves will cover the same path. It implies that suppose we think about the wave which one is coming out from L and M, then here this is the path difference between those two waves, and that is of the order of lambda by 2. So for the wave coming out from N and L, the resultant path difference that will be of the order of lambda. એવું એટલા માટે થાય કે M અને N માંથી જે waves diffract થઈને બહાર આવે છે એ બે વચ્ચે પણ path difference lambda by 2 હોવો જોઈએ. ને possible તો જ થાય કે આ lambda by 2 હોય તો આ પછી lambda thatu hoy. Okay, so now from figure we can write sin theta, that is equal to this opposite lambda upon this hypotenuse A. Now theta is very small, so we can write sin theta, that is nearly equal to theta. So theta, that is lambda by A. Okay, now path difference at point P, lambda, that we can write this lambda, that is equal to A theta, and that is for first minima. That is for first minima. Okay, or say simply you can write this one like this also. Sin theta, that is if you take this particular side, then sin theta, that is this side opposite, that is lambda by 2, and this one is now the hypotenuse, that is half part of the slit, so divided by A by 2, so again you will get the same thing. Okay, so theta, that is lambda by A here. Clear to all of you? Now on either side of first minima, there is the maxima, which is first maxima. Okay, now for first maxima we can give the explanation like this. Some waves are diffracted at such angle theta dash so that the slit behave like divided in 3 parts. So in that particular case, see the figure that will be like this. Can you see? And here see, the slit behave like divided in 3 parts. So for first part here, see, the path difference, that is lambda by 2, for second one lambda, and for third one 3 lambda by 2. In this way the slit will behave. Clear to all of you? Now if we give the mathematical explanation for this, then we can write sin theta dash, which is nearly equal to theta dash. So for that, opposite here, that is lambda by 2, and on this side the hypotenuse, that will be A by 3, because 1/3 part of the slit that we have to consider. Now in this case, when we consider here 3 part of the slit, then as discussed, for these 2 part, the waves diffracted from part 1 and waves diffracted from part 2 will cancel the effect of each other, and we will get the intensity only due to superposition of the waves which are diffracted from third part only. So intensity, that is very less due to that reason. So here we can write now theta dash, that is equal to 3 by 2 lambda by A. Then second minima on either side. So for second minima we can give the explanation like this. Some waves are diffracted at such angle theta 1 for which slit behave like divided in 4 part. So here if we consider 4 part of the slit, then for first part lambda by 2, then second part lambda, then for third part 3 lambda by 2, and then for fourth part 2 lambda. In that way we can represent the diffracted waves. So simply we can say this thing: the waves which are diffracted from first 2 part of the slit cancel the effect of each other, and similarly all those waves which are diffracted from third and fourth part of the slit will also cancel the effect of each other, and therefore resultantly we get the minima at the point of superposition of all these waves. Now for those waves, if we write sin theta 1, then that is opposite for this first part. So lambda by 2. but this hypotenuse. So here now we have to consider 4 part of the slit. So first part that will be a by 4. So we can write therefore theta 1 equal to 2 lambda by a. Clear? Now see, for first minima, theta equal to lambda by a. For second minima, we have 2 lambda by a. Suppose we think about third minima. So in that case, we have to consider 6 part of the slit. So અહીંયા તમારું theta 2 એ 3 lambda by a આવશે. Clear? પછી એવી જ રીતે અહીંયા જો તમે સેકન્ડ મેક્સિમા લઈ લો તો હવે આ ફર્સ્ટ મેક્સિમામાં તમે 3 પાર્ટમાં ડિવાઈડ થયેલી ઇમેજિન કરી હતી સ્લીટને. Then for second maxima we have to imagine it is divided in 5 part. So 4 part will cancel the effect of each other and the intensity on the screen will be obtained only due to all those waves which are diffracted only from that 5th part. એટલે એની intensity હવે હતી એના કરતા first કરતા બી ઓછી આવશે. So for that here you will get theta double dash, that is 5 by 2 lambda by a. So now in general we can write the condition for minima, that is theta equal to n lambda by a, and condition for maxima, that is theta equal to 2n plus 1 lambda by 2a, and here n equal to 1, 2, 3 and so on. So in this way we can give the explanation for the intensity distribution on the screen in diffraction pattern. Clear to all of you? In the double slit experiment, we must note that the pattern on the screen is actually a superposition of single slit diffraction from each slit or hole and the double slit interference pattern. This is shown in figure. It shows a broader diffraction peak in which there appear several fringes of smaller width due to double slit interference. The number of interference fringes occurring in the broad diffraction peak depends on the ratio d by a. That is the ratio of the distance between the two slits of the width of slit in the limit of becoming very small. The diffraction pattern will become very flat and we will observe the two slit interference pattern.